Okay, hello everybody. Last week we started talking about why we are studying operating systems, and we tried to define the operating system first. Instead of giving a direct definition, we said that there are two main reasons why we are using operating systems. First, operating systems abstracts the hardware. The abstracts the hardware, hides the details of the complicated hardware from the ordinary users. That is the first reason why we are using the operating systems. And then second, we are using the operating systems to make resource management, because the hardware is very complicated. There are many resources. Most of the resources are very large, and they need to be shared fairly and efficiently between the processes that is using those resources. That's what we said for the main reasons why we need operating system as software. And then, given that definition, we started talking about the history of the operating systems, how it started, and how it developed. And we said that operating system development and the history of the operating systems follows the development of the computer hardware, really. At the beginning, we didn't have operating systems because the computers are not that powerful enough to support another piece of software running at the same time with the other programs, okay? But when they realize that the software can help other software to use the computers in an efficient and more effective way, and the computers are more powerful enough so that I can support running more than one program at the same time, the idea of compilers and operating systems became more attractive, and people started coming up with ideas for the operating systems. And we said that with the third generation operating systems, the ancestors of Linux, Unix operating system, Multics, and the ideas of multi-programming, time sharing, spooling, real-time systems, and the protection, they came up, and people started doing that kind of stuff. And we continued, and we talked about today's operating system environments. We are talking about the mobile operating systems. We are talking about the battery management. We are talking about the user interactivity, etc. So that was kind of the summary of what we did last week. Let's continue with our discussion. Chapter number 1 again. Chapter number 1 is talking about the general concepts of operating system. Let's talk about the computer hardware. Why are we talking about computer hardware? This is operating systems course, and we are talking about computer hardware, which is really the subject of computer architecture course, actually. But operating system, as we said before, one of the tasks of operating system is to hide away the details of the computer hardware. So we need to know about the computer hardware to some extent, so that we know what we mean by hiding the details away of the computer hardware. Also, the operating system, although it's a piece of software, it works very closely with the hardware. That's why we need to know about the hardware. Not maybe in very, very detailed way, but maybe in general terms. So we are making a survey of hardware systems, of hardware subcomponents of a computer. Okay, this is a very simplified architecture of a computer system. We are showing you some of the components. At the center we have our CPU, and that CPU is connected to the other hardware components of the overall system using a bus, very simple bus. As I said before, this is a very simplified picture. More realistic and modern pictures will come up later in today and later in the semester. And the CPU is connected with the memory and the other controllers using this bus. That's what we said. What is MMU? Can anybody tell me what MMU is?
Cache, maybe cache.
Cache, you mean, Şevki? No, it is not cache.
Memory management unit.
Memory management unit, yes, MMU. Okay. So why is MMU is in the CPU, not in memory? Okay, that's a good question. Why are we putting this small piece in, and as you have noticed, it is on top of the bus. Okay, so this MMU is responsible for making the virtual memory possible. Okay, it makes the virtual memory possible. Without the virtual memory, the idea of the virtual memory, current operating systems wouldn't work. The virtual memory is this. Okay, each process running on the CPU, they think that they are the only owners of the CPU. They are using the CPU and there are nobody else. Okay, so they think that the whole memory it belongs to them. So when they address a memory location, they think that it is their location and they don't have to share the memory with anybody else. So this MMU makes this possible actually. MMU makes our processes think that they have all the resources, they have all the memory to themselves. And we are going to talk about the memory and the MMU in chapter number 3 of this book. And it's going to take us maybe 3 weeks or something like that. So it is a detailed small box. Okay. So MMU is there, and we have our memory, main memory of the system, and we have bunch of controllers. These are electronic devices. As the name says, this is all hardware. Okay. In this picture, there is no talk of software. Okay. So this is controller. These controllers are electronic devices. They act as an interface between the system bus and the actual input-output device. In this case, it is the monitor. In this case, it is the keyboard. In this case, it is the printer. In this case, it is the hard drive. Okay, so that controller is an electronic device that kind of acts as a translator of electronic signals between the bus signals and the electronic devices signals. Okay, and these controllers, they have registers in them, many registers sometimes. Okay, they have their own registers, and you communicate with these controllers by writing to these registers and reading from these registers. Okay, you will say that, let's say these are my, I am just making these up, A, B, C, D registers. Okay, you will say that I am writing 10 to this register. That means that read some data from sector number 200, okay, of track 100, and put them in this address, etc. Okay, so you are communicating with this hard disk by writing to these registers and reading from these registers. But how would you know what to write to these registers? Okay, and how would you know where to read this data? The bad thing is these number of registers and the meaning of these numbers changes from hard drive to hard drive, from manufacturer to manufacturer. So how am I going to know all that details? That's why we have drivers. Okay, each input output unit, okay, each controller, they have their own driver software, which is most of the time part of the operating system. Okay, part of the operating system. So as I said before, I don't want to talk about software in this slide because this is about hardware, but I cannot because this is operating systems course, and from time to time I need to talk about how the operating system communicates with this kind of stuff. So that's what we mean by hiding away the details of hardware. Okay, I have never had to know about these registers when I try to open a file using my C program or even in fact the assembly program. All I say is that open that file. That's it. Okay, so we talked about the controllers. Each controller is specialized and they have lots of registers and memory buffer locations. And when we come to the chapter number maybe 5, I guess, we will talk about the I/O, input output, and we will talk about the controllers and the specialized hardware a lot in that case. Okay, let's move on. Let's talk about our most important hardware component, processor. Okay, it is the brain of the computer, as we know. Why we call it the brain of the computer? Because it is the part that executes all the instructions. It makes all the calculations. And as you know from your computer architecture course, okay, the CPU has phases while it is processing all those instructions. It fetches an instruction, it decodes it, instruction, and it loads the required data from the memory, and it executes all those instructions, and it repeats it. So for each instruction, depending on the system architecture, I have fetch, decode, execute phases, and some processors have more phases, but let's keep it simple for this case. Let's say we have only 3 phases. Okay, we know this. And can anybody tell me? Can anybody tell me why we have these phases when we are processing the instructions? Why did that design and when we process an instruction, why did they design the processors to have these 3, 4, 5, whatever phases?
In order to pipelining.
Somebody said in order to have pipelining, and that's right. When you have pipelining with a processor, you are in fact making your processor 3 times faster. Why? Because when you are executing an instruction, you might be decoding another one and you might be fetching another one. So that means that your CPU is handling 3 instructions at the same time effectively. So you may have up to 3 times speed up. Okay, so another important thing about the CPUs are registers, right? Each CPU should have registers, and there are many registers depending on the CPU. Like the data registers, you load some data to your register, you read it, you write your register data to memory, and you load data from the memory to your registers. They are designed that way. There are some specialized registers, and these are common with all the CPUs. One of them is the program counter PC, which is very important. Okay, which is very important. Why? Because program counter points to the location of the program where the CPU is executing the instruction. Okay, program counter holds a pointer, and our CPU, when it fetches the instruction, it fetches the instruction from this program counter pointer. Okay, another important register is a stack pointer. Stack pointer is so important. Why? Because we keep, do you remember the program that I showed you before? Let me try to find that program again. I think it was in like that. Was it in here? Yeah, test.c. Okay, let's test.c. As you see, I have 2 local variables, I and k here. I and k are my 2 local variables, and the local variables are kept on my stack. Okay, let's look at this test.s, which is the assembly version of this program. Maybe use, okay, less is good. Okay, this is the beginning of the main function in my assembly. As you see, this one says that minus s means that go to 8 bytes lower than the stack pointer and load 0 to that. And this one says that load this value to my register EAX and move this value to this position beneath the stack pointer. So stack pointer is pointing to the top of the stack, and below that stack are my local variables, and I refer to my local variables using this notation: -4, -8. If I have more, I will have -12, etc. That means that each of my integers are, if each of my integers are 4 bytes, right? That's what it says. Let's do this then. Test.c. Let me try to make this long integer. My I is a long integer, and let me put a special number in it so that we would know. Okay, let's compile this. GCC -s test.c. Okay, I did not include that std lib stuff. And let's look at the test.s. Okay, see, it is -8 now. It is not -4, it is -8. I made the long integer. Long integers are 8 bytes long, right? And 16 is here. Good. So I am talking about this because why are stack pointers important? They are important because we keep our local variables in our stack space, and locals are very important for us because most of the time when you call a function or method, you keep your data as local variables, or you keep your arguments, function arguments, okay, method arguments in your stack. And to refer to those locations, then you need to use the stack pointer. For the global variables, the things are different. For the global variables, let's look at this. Okay, let me get rid of this. No, well, let stay it in here. Okay, integer global is 64. Let's see where that 64 is going to go. Okay, but I think let me see if the less is going to work. Yeah, see, there is a global global variable, and it is not in the stack, and it looks like I have a label for it. Yeah, that's nice. And I loaded 64. These are all assembly instructions. Okay, so my assembler is going to reserve some space in my heap and put these numbers 64 in that location. It is not in the stack. It is not in the stack. What happens? Well, I am spending too much time on it, but just to make you kind of curious about what is going on with this kind of stuff, and I think you should do this yourself. So I am going to increment global by 1. Let's see what kind of code I am going to get. Okay, 64 is here. So yeah, see this one. It loads the global to my register and it adds 1 to the register and it puts it back to the global. So global has its own address. For the globals, you don't use this stack pointer -8 or something like that. So it is a global address. That's why We don't like globals much because its address is fixed. With the locals, no, it is not fixed. It changes position. That's why we have the recursion available. Okay, good. So you make these kind of experiments yourself to understand what's going on with register and the CPU, etc. No programming language will let you change the stack pointer or the program pointer or any other register using the programming language structs. Even C will not let you do that, okay? If you like to play with the registers, okay, move them around, put them in a memory location, get them back, etc., directly, or increment the stack pointer by 1, etc., okay? You need to use the assembly language or the machine code. No program, no C program will let you do that. Of course, with the C, it is more possible because, as you see, I can do this kind of stuff. I can interpret it. I know what C is going to think. Okay, C is a very nice language in that sense because it's a very simple language. I know what it does. Okay, another important register is the program status word. Okay, it includes the condition bits, kernel mode, CPU priority, etc. What are the condition bits? What are the condition bits?
Flags for checking equality.
Yeah, for example, the flags for checking the equality. After I say that if this register value is 0, then I need to check those flags, all right? Jump not equal, etc. So those are the condition bits. They are hidden in the, they are stored in the program status word. Also the kernel mode, okay? The kernel mode, am I in the kernel mode or am I in the user mode? You look at the program status word for that one, or the CPU priority. What is my priority right now? Is it high priority, low priority, etc.? These are all stored in the program status word, and the information, the exact information kept in this word depends on the CPU type. Okay, so this is the CPU. So how do I change my kernel mode? If I am in the user mode, I like to go to kernel mode. What would I do? You cannot do it directly. You cannot say that change my mode to kernel mode. No, what you need to do is you need to make a system call. Okay, you need to make a system call. System call is a entry point for the operating system, and there is a special instruction for the system call. Let me show you that one. Remember that exit thing that I showed you? Yeah, well, this one, yeah, this one just calls the exit routine, but I don't see exit routine because it's a part of the library. That's why I use this dump stuff. Let me do this test static, yeah, by dumping it. So this one is very large file. How large is it? Let me try to find how large. So it is 200,000 lines, okay, of dumped code. This is my test a.out, and I like to find the system call SVI. Okay, see, this is a typical system call. It is moving some stuff to registers, okay, setting up the registers and diving into the system, okay, call to make a system call. So when the system call is done, I trap to the operating system, and operating system says that, okay, operating system says that, okay, somebody's calling me. So this is a special call, like a function call, but it's an operating system call. It's a system call. operating system receives this call, and now operating system is running, and operating system is running in the kernel mode. Okay, so this is how you switch to kernel mode. You cannot switch to kernel mode automatically by yourself. You need to make a system call. When you make a system call, operating system has the control of the CPU now, and now the CPU is in the kernel mode. Whatever you wanted from the operating system is going to be performed, and you are going to get your results back. Okay, good. So we are going to look at this process even in more detail in a few minutes. Any questions so far about the processor? You know the types of the processor, you know all those phases of the processor instruction execution. You know the hazards, right? This is complicated stuff. You know the caching, and you have written MIPS code before, and you know most of this stuff. We are just repeating it. We talked about pipelining. We said that each CPU. Is there a question?
Yes.
Sure.
What I was wondering is, didn't we have a flags register for condition bits? Why do we use the program status word for that?
Program status word is the general name to keep that kind of information, and the specific CPUs might name that information flags register or that kind of stuff. Okay, so PSW is the general name that keeps that information. Depending on the CPU, it could be called flags register or something else. But that information has to be there, okay? The condition bits, kernel mode. Very simple CPUs, they don't have the kernel mode because they don't have the protection. Very simple CPUs, they didn't have the CPU priority. Okay, good. Any other questions? CPU pipelining, we know this. Fetch, decode, execute. And since this is pipelined, again, this is fetch, decode, execute, and fetch, decode, execute. Fetch, decode, execute. So when you look at this time unit, you see that the fetch hardware, decode hardware, and execution hardware, they are all busy. So I don't leave any part of my CPU idle. I always keep it. So 3 times more speed overall in effect. Okay, so this is a simple pipelining architecture. There are more complicated pipelining architectures. Okay, superscalar CPUs, they have stuff like that. They have more than one fetch unit, they have more than one decode unit, and they have many execution units. Okay, and the architecture could be as complicated or more complicated than this. Okay, so the CPU is able to fetch more than one instruction at the same time, decode more than one, and since there are many there might be some dependencies between these instructions. Okay, I put them in a holding buffer, and the hardware is smart enough to assign executions units for each instruction waiting in the holding buffer, and each instruction might depend on the other one. There might be some hazard handling stuff, you know, all of these, and this is more complicated. Okay, and if the compiler that produces code for this kind of architecture knows architecture very well, it can take advantage of the pipelining structure of the CPU. For example, you know that if you fetch an instruction and if you see that it's a jump instruction, then you need to invalidate your other units, right? Because you know that the next ones are not going to work. So you need to invalidate the other units after you realize that you are going to jump. Some compilers are smart enough that after the jump, they produce code to start executing stuff from the top of the loop. Okay, so those are the those are the those are the tricks that you can play with your compilers and the CPUs to make the overall system more efficient. Okay, another topic that we see more often is multi-threading and multi-cores with the CPUs. Okay, well, we don't have this rule anymore, unfortunately. Moore's law. Okay, Moore, he is one of the founders of the Intel Corporation. He said that in 1970s, he said that every 18 months, okay, we are going to have 2 times more transistors on the same area of chip space. Okay, so that's exponential growth actually. 2 times more transistors. More or less, this went on for 35 years. Nowadays we are not getting that much more transistor every 18 months. Part of the reason is our transistors are so small. Okay, now we started talking about the material molecules. Okay, very, very small stuff. The second reason is we don't have to, right? I mean, I don't need, for my general use, for my everyday use, I don't need any computer that is faster than this one. Or I don't need more memory that is faster, more larger than this one. Of course, I mean, if it is the same price, I would buy a much faster and much larger capacity stuff. But I mean, if the memory is 64 gigabytes and if it is value is $2,000, I wouldn't pay money to it because this is good enough for me. So this is what's happening for the last 5 years maybe. So they are not putting more transistors or making it faster. Instead, what they do is they keep putting more cores in the same CPU. Okay, so you don't have a single CPU on your chip. They put more than one CPU. Okay, so instead of making it faster or more transistors on the same CPU, they say that okay, let's make it parallel. Put more CPUs, put more cores on the same chip. And GPUs are taking this idea to the extreme. GPU means that graphical processing unit. They put thousands of processing units on the same chip. Okay, they are able to do that with the GPUs because GPUs are simpler than CPUs. Okay, GPUs are simpler than CPUs, so they can make thousands of them on the same chip. So if this is the idea, if my processor is able to do that kind of stuff, then as an operating system, I need to hide the details of such CPUs, and I need to make the sharing of all these resources available to the user. Okay, so operating system has to know about these multi-threading and multi-cores. Okay, here's one example, 2 examples of the multi-core architecture. I have 4 cores on the same CPU on both sides. The difference is each one has their own cache. Okay, each one has their own L1 cache, level 1 cache. But in the second architecture, each one has their own level 2 cache too. In the first architecture, level 2 cache is shared. Level 2 cache is shared. If the cache is shared, that's good. Okay. If I need to communicate between these two cores, then I can use the L2 cache. Okay. So that's fast. This one is not going to do that communication using the cache. Each one has to refer to the main memory, and that's going to take more time. And we are going to talk about the speed differences between reaching your cache and reaching your main memory. Okay. Good. So these are the things that we are going to talk about the CPU, and these topics will go more often, and we will talk about multi-threading, multi-cores, and etc. Very often in our next chapter when we talk about processes. Good. Let's talk about the memory. This is how I like our memory. Our memory should be fast, large, and cheap. Give me very large amounts of memory. It should be fast, very, very fast, and it should be very, very cheap. Okay. Unfortunately, the world is not like that. Nobody is going to give you everything. Okay. If it is fast, it's not going to be large. If it is cheap, it is not going to be fast. Okay. If it is large, then it's not going to be fast or cheap. So you cannot satisfy all of these at the same time. And in fact, this is the hierarchy of the typical memory. Okay. At the top we have the registers. Registers are very, very fast. Okay. In a single clock cycle, I can do reading, I can do writing of the registers. Very, 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 very fast. Okay. But their sizes are so small, less than 1 kilobyte at most, typical capacity. Okay. And then I have my cache, L1 cache or L2 cache. Okay. Cache is not as fast as register, but they are not bad. Instead of 1 nanoseconds, I have 2 nanoseconds now. And their sizes are larger. They are slower, but they are larger. Okay. And then I have my main memory. Okay. So as you see, accessing the main memory is 10 nanoseconds. This is 10 times slower than accessing your registers. But my main memory is large. Okay, we are talking about now gigabytes. And then, so main memory is slower, but it is larger. If you like to go even larger, you have your magnetic disks or magnetic tapes, but they are even slower. Okay. Okay, what is the difference between nanoseconds and milliseconds? Okay, it is million times slower than the main memory. Okay, so if you like to go large, then you need to go slow. If you like to go cheap, magnetic tape and disk is cheap, then you have to be slow. And the management between all these has to be done. What was the task of the operating system again? Managing the resources. It has to be done by the operating systems for the computers. Okay. Okay, let's look at these registers and cache. What did we say? We have only small amount of registers. For 32-bit systems, there are 32 registers usually, and the size, of course, the size of each register is 32 bits. For 64-bit systems, there are 64-bit registers. So when you access the registers, no delay. Every clock cycle you can access them, write them. So keep your data in your registers, and you could be as fast as possible. But the thing is that you don't have that much registers. And then if you cannot fit your data, your instructions, your data in your registers, then you have your L1 cache. level 1 cache. We are talking about now kilobytes. If it is not large enough, if it doesn't fit in your L1, then you have your L2. So who does this task of keeping your data on L1, L2, and etc.? Usually it is done by the hardware, okay, and you have seen examples of cache management algorithms in your computer architecture course, right? You have seen examples of cache replacement algorithms, and we are not going to talk much about cache replacement with the CPU caches. But when we talk about the virtual memory, similar kind of problems will occur, and we are going to solve them, and we are going to use similar ideas to do virtual memory management. Okay, good. So these are the registers. So I think I talked about this. I'm not going to talk about it. If I move to the disk side, okay, they are of course larger, cheaper, but then they are slower than the main memory. The disks are slower because they are mechanical. Okay, they are mechanical. There is a spinning disk, spindle. Okay, sometimes many magnetic disks spinning on the same spindle, and there is a mechanical arm that moves around and that reads your data. And I think I have a disk around. Let me find my desk. Okay, this is the desk. Okay, this is the arm that moves around, and this disk is spinning, right? And then when I move this around, I can access it where I like. And usually there are more than one. See, there is only one disk here. There are usually more than one disks, okay, with space in between, spinning around. For some systems, this is spinning like 30. I don't have the coffee, but orada hocam alt tarafta bir yerlerden alalım. This is spinning very, very fast, sometimes 10 rotations, 10,000 rotations per minute, 15,000 rotations per minute. But again, it doesn't matter how fast they are, it is mechanical, so it is slower compared to your memory. Okay, so who's going to again manage the data going between your main memory and the disk? It is the operating system. Okay, also how do I manage the storage on the disk? It is the operating system. And how do I provide the protection between the files and the different users of the disk? Operating system. Okay, so we are going to spend lots of time explaining these. You might say that well, we are not using the disks anymore much because we have the SSD, solid state drives, right? Yeah, that's true. Most of the computers, especially the personal ones, they don't use these kind of mechanical disks. They have solid state drives. They are all full electronic. There is no moving part in them. They are much faster. Yeah, that's true. But again, they are slower than the main memory. Okay, they are slower than the main memory, and they are larger than the main memory. And usually, many systems they use a combination of SSD because SSD is still more expensive than hard drives. SSDs are between the main memory and the hard drives in terms of their capacity, how large they are, and in terms of their speed, and in terms of their prices. Good. Okay. Okay, here's an example of multi-disk hard drive. I have 1, 2, 3, 4 disks. and these are the read-write heads. And in this picture, the read-write head is here. Okay, I don't know if you can see it, but there is a read-write head under the desk and over the desk. Can I focus in here? Yeah. Okay, this one is very close to the desk. I can move it around. Okay. Okay, of course this is a dead desk. I shouldn't be I cannot do the same thing to running desk. Okay, this is a old desk. This is dead long time ago, and very small capacity disk too. I don't know how small it is, but maybe a few megabytes. Yeah, I'm talking about megabytes here. Okay, so we are going to talk about the disks, so they are still relevant. The book is going to tell us that we will talk about obsolete systems. I mean, we will talk about history a lot. Why? Because history is important one. The second is usually whatever we have solved in the past, we are going to solve it again for the new technologies. Why? Because when we started in 1950s, when we started using computers, they programmed their computer using the assembly language because there were no compilers, there were no operating systems. Why? Because the computers are not powerful enough to hold a compiler and operating system. Okay, there is no compiler, so you write everything in your assembly. We are kind of doing the same thing with nowadays with our embedded systems. Embedded systems, the CPUs are so weak, CPUs are so unpowerful, we may not find good compilers for them. Okay, so or we need to write very careful code, so we write everything in assembly. So whatever they did in 1950s, we are doing the same thing with the very weak computers for today's. Okay, so studying old systems is a good way to understand how the operating systems work. Also, it is a good way to get ideas for the newer, less capable systems. Okay, so we are going to look at the disks. That's why. Again, let's go back to I/O devices. Disks are specialized I/O devices. They are used for replacement for memory if the memory is not large enough. But there are many other I/O devices. Okay, and as we said before, controller is part of the I/O device. Okay, it knows about the I/O device itself. Also, it knows about our system structure. It knows about our bus. So it acts as an interface, a hardware interface between the I/O device and the computer system. And who controls this controller? It is the device driver. Device driver is the middle layer software for device controller by the manufacturers. Usually if you buy let me put, okay, if you buy a hard drive, okay, either it comes with its own hard disk controller, it used to be like that in the old days, or it uses standard disk controller, but whoever built this hard drive, they provide the driver software for this hard drive. So when you install that driver software to your operating system, now your operating system knows how to communicate with the hard disk drive, because that operating system calls the functions of that driver. Since driver becomes a part of the operating system, it has to be written very carefully, because if it fails, it's going to fail the whole operating system, and that's not a good thing. So you shouldn't make any driver part of your operating system if you don't trust that driver. So driver is piece of software, controller is a piece of hardware. Always keep this in mind. That's the main difference between those two. Okay, any questions so far? Do you have any questions? Okay, if there are no questions, then I will take 10 minutes of break. And after the break, we will start talking about how do we do the input output procedures actually. Okay, so let's be here around 11:32. Okay, 10 minutes. Hadi görüşürüz. Ben gönderirim olmaz. Okay. Let's continue. Let's see very small, very superficial introduction to the I/O devices, how the I/O is done. There are three ways to do I/O. One is busy waiting, 1, 2, 3 interrupts, and the direct memory. Let's look at how this busy waiting works. With the busy waiting, you do this, okay? With the busy waiting, CPU using some kind of a mechanism puts these numbers into the hard disk controller. Okay, it says that I need data from this sector, from this track. Okay, get this data. Since hard disk drives are millions of times slower than the CPU itself, CPU has to wait in an idle loop. It is waiting in a loop, in an idle loop. And it is trying to check, and every time, let's say there is a register here, and if this register value is, let's say, 1, then everything is red. If it is 0, it is not red. So this CPU is waiting in a tight loop, okay, for this register to become 1. Okay, this is how busy waiting works. So CPU is busy waiting for this hard disk drive to complete its data transfer. When the data transfer is okay, then CPU can take this data, move it to this main memory, and use it from there. Okay, so as you see, this is very inefficient. This is very inefficient. Why? The CPU has to wait. The CPU has to wait until the data is ready. So it is wasting billions of CPU cycles. Okay, it is not acceptable for the mainframe computers. It is not acceptable for expensive computers. Why? Because I am wasting the valuable CPU time, and while the hard disk drive is working on its job, everybody else, if I am doing multi-programming or time sharing, everybody else is waiting for that one. That's not a good thing. So they say that, okay, this is not going to work that way. Still, busy waiting is still used today. Why? Because it is a good way of doing the I/O for embedded systems, for very small systems, for specialized computers. Okay, so busy waiting is not an old I/O method. It is still being used today. It is preferred for some special cases. And then we have interrupts. Interrupts work this way. You program the I/O device. You said that, okay, again, write the registers of the I/O device. I need this and this data. Okay, now I am going to go to sleep. As a process, I am going to go to sleep, and wake me up when the data is ready. When I say I'm going to go to sleep, the CPU doesn't go to sleep. The process goes to the sleep. Okay, process tells the operating system that I need this data, and the process goes to sleep. And the operating system programs the I/O controller, and it lets another process run. So another process is running while the hard disk drive is working on that request. When the data is ready, okay, hard disk drive causes an interrupt, and that interrupt stops the CPU, and that interrupt is handled by the operating system, and operating system knows that the data is ready, and it wakes up the original process that asked for the data. Okay, so that's how the interrupts work. So I need lots of hardware help, specialized interrupt handling hardware but you know how the interrupts work from your architecture course. And the third one is the direct memory access. Okay, so the problem with the interrupts is this. Still, CPU has to transfer the data from the I/O controller to the main memory. So I am wasting CPU time to moving the data around. That's not a good thing. Okay. Instead, they have this direct memory access. Direct memory access is a step further development from the interrupts. Okay. The CPU sets up the DMA chip. DMA chip, direct memory access chip, is another computer hardware. Okay. It programs the controller. Telling what it needs. Okay. When the data is ready, it makes all the data transfer from control to the main memory. Okay. And it informs the operating system that the data transfer is ready. So the CPU time is not wasted for moving the data around. It is more efficient in terms of CPU time, DMA. Okay, so three things, three types of input-output methods: busy waiting, interrupts, and direct memory access. We will be talking about this a lot. Direct memory access, other than the direct memory access method, everything, all the data movement, all the programming are done by the CPU. Okay, CPU has to be involved in this I/O stuff. With the direct memory access, this programming of the controller and the communication with the controller is handled by the DMA chip itself, but it makes the overall hardware a little bit more complicated. Okay, here is an example for interrupt handling. Okay, I talked about the busy waiting. The CPU programs the disk controller. What did I say? The disk controller has registers in them. It puts special values 10, 20, 110, etc. Now this controller knows what the CPU wants. Okay. After that, the disk controller starts working with the disk drive to satisfy this request. Okay. CPU doesn't sit idle. Okay. CPU programmed the disk driver. CPU is now in the control of the operating system. Operating system now lets another process use the CPU. When the data is ready, CPU is busy with some other process. When the data is ready, it lets the interrupt controller know that the data is ready. Interrupt controller interrupts the CPU and it passes the address of the passes the information about the interrupt happened. They say that, okay, this is a disk interrupt, okay, and these are the additional data. Now the CPU is again controlled by the operating system. Operating system runs the interrupt handling routines to handle this interrupt. So no CPU time is wasted while waiting the disk drive to complete its operations. Okay, this is the part of the picture in terms of what's happening with the software. Okay, so when the interrupt happens, here number 3, when the interrupt happens, when the data is ready, my instruction is interrupted as a process, regular process. My instruction is interrupted, my execution is interrupted. I go to the operating system. Okay, it is done by the hardware. Okay, hardware says that, okay, whatever you are doing, I'm going to stop. Now operating system runs. Operating system takes this information about the interrupt happened. Okay, there could be tens of different types of interrupts. It could be a keyboard stroke, mouse event, network event, disk drives, whatever. Okay, many different types of interrupts. Operating system determines the hardware determines the type of the interrupt, and it chooses. Okay, there are many boxes here. it chooses the appropriate interrupt handler for that interrupt type, and it executes it. That interrupt is handled, and then I return with the next instruction. Now I am not in the interrupt handler anymore. I am not in the kernel mode anymore. I can go back to my next instruction. Okay, so whoever is running these instructions, they even don't realize that they are interrupted and they are continuing back. Okay, so this is what happens in terms of software. Software doesn't know that an interrupt happened and it is handled by the operating system. Good. Any questions?
May I ask a question?
Sure.
For the CPU, for example, there are many interrupts, but which process should process which interrupt? Where is it written?
There are many types of interrupts. For each interrupt, there are specialized interrupt handling functions in the operating system area. Okay. Whoever designed and implemented the operating system says that if there is a disk interrupt, you are going to call this. If there is a keyboard interrupt, you are going to call this. If there is a mouse interrupt, you are going to call this. Okay. That interrupt handling routine is special, and usually it communicates with this controller using these registers, and it handles that interrupt. So how do I handle a disk interrupt? Usually when the disk interrupt happens, the data is ready. So you need to take all the ready data from disk controller's memory to the main memory. That's what you do. When the mouse interrupt happens, what you're going to do is you are going to get the mouse coordinates from the mouse controller to the main memory wherever it is needed. Okay, so this.
But I asked the process side. For example, there are many processes, and each process will use. For example, there are two processes. Both of them is using the mouse.
Oh yeah, okay. Yeah, so you're. That's a good question actually. You are saying that there are three processes, and each one is waiting for their data from the disk drive, right?
Yes.
One is saying that, okay, I'm going to read this file. The other one says that I am going to write to this file. The other one says that create a directory for me. Three things happening at the same time, right? Okay, yeah, that's good. So it is the task of the operating system, okay, to know which process is waiting for which disk drive job. Okay, so operating system knows it. It keeps tracks of. It keeps tracks of which one is doing what. The disk drive can do only a single thing at the same time. It can read or write or do some kind of operation. So operating system puts them in a queue. It say that, okay, the disk drive is handling the job of this process. When that job is done, I am going to let the process know that its job is done. You may take your data, okay? After doing that, operating system ask the disk drive again to do something else. Okay?
Okay.
So it puts the queue. So that's what we call resource management. That's a very good question actually, Ebru. So when we say resource management, there is only one disk drive, there is only one mechanical arm that can rotate. I cannot read two things at the same time. I can only read one. But there are 5 processes asking for input output with the disk. So this requires resource management. Who is going to use the disk? Okay, because I am using the disk in a time multiplexing chain, right? So I am going to put you in a queue. First you are going to do, then you do, yeah, then you do, then you do. Okay, so each one is waiting for their turn, and they are all blocked. All these processes are blocked until their jobs are handled by the disk drive, and that's called the resource management. And that's not going to happen with the disk drives only. It's going to happen with the network drives, because there are many processes using the network, and it's going to happen with the memory. It's going to happen with the printer and etc.
Okay. Thank you.
Thank you. Any other questions? Good. Okay, let me move on then. Let's talk about more about this interrupt stuff. This is important, interrupt versus traps. There are two ways to switch to operating system mode or the kernel mode. One is the interrupts, okay? When you are running an instruction, a regular process in the user mode, okay, if an interrupt happens, you switch to, the CPU switches to the kernel mode automatically because interrupt has to be handled immediately, okay? What are the reasons for interrupt? Yeah, tell me something, okay? It could be a disk drive interrupt, it could be a keyboard interrupt or the mouse interrupt, or most importantly, it could be a timer interrupt. Timer. Remember the timer? Every 100 times a second, a timer interrupt happens. And each time when I am executing an instruction, a timer interrupt happens. The operating system mode, okay, I am in the kernel mode of the operating system now. That timer interrupt has to be handled. What does the operating system do? Operating system says that, okay, this is a timer interrupt. I am going to measure how much time this process has used. Should I do anything other than the time management? Yeah, sure. Operating system does many other things. We are going to see it in the next chapter maybe, okay? And after that, I am going to go back to the next instruction, okay? So the timer interrupts are the most frequently occurring one. Other than the timer interrupts, of course, there are many I/O devices and they are causing interrupts. So this is one way to go to the operating system, okay? This is the first way, an interrupt happening. The second way is the traps. Trap is system call, actually, okay? I showed you this, right? Why did I close it? Come on. Okay. It's classes and what did I say? VI test statics S, and I think I was system call, right? Do this 7, yeah, system call. If you execute this instruction system call, you directly go to the kernel mode, okay? So let's look at this simple C function call. I am calling the function read with the file descriptor, my buffer, and the number of bytes. So you are saying that I am saying that I have an open file. Describe this file descriptor. I like you read n bytes from the open file into this buffer. That's what you are saying, right? You know this from your C course, okay? So that's what happens. This is the code produced by your compiler. It pushes the n bytes to the stack. It pushes the starting address of the buffer to the stack. It pushes the FD to the stack, and it calls the library function read. Okay, it calls the library function read. Library function again is in the user mode. It's not your function. It comes from the standard library. Okay, it says that okay, somebody is trying to read something from a disk file. I cannot do it myself because it's an I/O operation. I need to ask help from the operating system. So it says that I am going to put code for read register, okay, and then I will trap to the kernel, making a system call like this one. This one says that okay, I will put all that information to these registers, and I am making a system call. This one is making a system call. When you make a system call now, it is the second way of switching to the kernel mode other than the interrupts. This is called trap. Okay. Now I am going to the kernel mode again, and there is a dispatching happening. Remember, there is a dispatch happened here. This dispatch is for the dispatch of the interrupt handler. This dispatch is the dispatch for the appropriate system call handler. So the operating system will find out of all these handlers, operating system will call the handler of the file read, okay, and that file read is going to do what? Is going to call probably a driver function, and that driver function is going to program the I/O device, and after that when I program the I/O device, then I know that there is going to be an interrupt. Okay, so I can go back to the original program, but original program is blocked. Why? Because it is waiting for this operation to happen. Then it is task of the operating system to switch to some other program. Okay, when the data is ready, all the interrupts are handled, then operating system returns to the original program. Original program says, okay, I'm done, I read all of my data, and it returns back to the original code. And by incrementing the stack pointer by 1, now I can whatever is returned, I can read it. Okay, so this is the process of making a system call. The time between this 9 and 6 could be very, very long, like 100 milliseconds maybe. 100 milliseconds means eternity for CPU. It is so long. Okay, it is so long. So between this 6 and 9, my original process is blocked. It is waiting for data to be ready. But as a programmer, you wouldn't know that. As a programmer, you would think that you make a call and your call is handled and you get your data back and you continue. But in between 9 and 6, maybe your CPU is used by many other processes we don't know. Okay, so this is the trap side. This is the second way to make an operating system switch to the kernel space operating system. Traps are the first way, interrupts are the first way, sorry. Traps are the second way. Okay, some people cause traps are software interrupts. Why do they say that? Because I am invoking the operating system call by myself. It's like an interrupt, but I am causing the interrupt myself. These are hardware interrupts. Hardware is causing the operating system to start. Other than that, operating system has no way of coming and taking the CPU away and using it. Interrupt has to happen, or a trap has to happen. Okay? Any questions? Good.
So just to be clear, we invoke traps, but we don't invoke interrupts.
No, yes, exactly. By we, I mean human beings or the programmers. But if you refer to we as I/O devices, yeah, our I/O devices cause the interrupt, hardware interrupts. People who wrote the programs, they cause the whoever wrote this system call is causing the traps. We are making a system call. Okay, some people say that. Okay, maybe I should ask you this. You don't need the timer interrupts actually. Some people say that. Why do they say that? Why are we using the timer interrupts? We use the timer interrupts so that if a process, this is one of the reasons, if a process is taking too much CPU time, it took the CPU and it is using the CPU for a very long time. Okay, when the timer interrupt happens, the operating system can realize that this process is using the CPU for a long time. I am going to let somebody else use the CPU, and this process is going to be blocked. Some people say that you don't need the timer interrupt for this. Can you tell me why?
Maybe there will be a lot of overhead copying happening after a process used a lot of CPU time.
What do you mean by a copying happening?
So registers and memory, etc.
So that's going to take even more time for that process to use the CPU. So the CPU is used by that process, right? Process is changing the registers and moving the stuff around, making lots of memory movements and etc.
Maybe a process has to invoke a trap to the operating system. It has to. What will be its job then? It has to read data from hard disk or use mouse.
Yeah, exactly.
It's an obligation.
Yeah, you cannot. The assumption is this: you cannot use the CPU all the time for a useful stuff, right? I mean, you have to go back. You have to ask for data. You have to write to disk. You need to know where the mouse is. Okay. You need to ask for more memory. Okay. Every time you need one of these, you need to cause a trap. When you cause a trap, when you make a system call, now operating system has the control of the CPU. It can switch to some other process. It can realize it. Okay, so that was the assumption, and in fact, the early versions of Windows, I guess, it didn't use this timer mechanism. Okay, it didn't have the preemption. The problem was this: some bad people write this kind of code knowingly or unknowingly. Okay, and inside this there is only this line of code. Okay, so I am just incrementing I by 1. I keep incrementing I by 1, so this code doesn't require any operating system help. I am just changing some memory location, and I can run this until infinity. So these kind of loops, infinite loops, cause problems for these kind of operating systems. Okay, so your system just hanged, it doesn't come back. So the only way to stop this loop from running is what?
Using timers.
Turn
Turn off your
secure.
turn off your computers. Some computers have this. Okay, when you run this kind of a code, okay, it is not giving up the CPU, right? You hit Control C on your keyboard, Control C. Control C causes an interrupt, and that interrupt is handled by the operating system. They say that stop whatever the process is doing. Okay, but usually whoever do this, especially for the purpose of hacking, they usually disable that Control C override, etc. Okay, so timers are important. Without the timers, we don't have any modern PC operating systems. We need timers, and you are going to see that we use timers other than this purpose. We need it for many housekeeping operations. Operating systems are complicated. Okay, they use timers to do other stuff.
What happens if, for some reason, due to some reason, there is no interrupt happening?
You mean there is a problem with the hardware?
Yes.
Well, then you have a broken computer. That's not a good thing. I mean, what you're asking is what happens if some part of the memory is not working, right? That's not a. Our assumption as an operating system is everything works perfectly. You cannot assume that. You cannot assume that. What happens if one of my registers are not working right? Then that's going to change everything. Sometimes operating systems are smart enough to handle some disk problems. For example, they may say that disk data from time to time may go bad. I am going to take some backups and etc. But with this kind of hardware, timer hardware, then they don't assume that kind of stuff. What I am saying is not exactly right, but I mean, we don't put those kind of guarding code for our operating system to handle these kind of hardware malfunctions. The hardware may go bad from time to time, but if my timer device is dead, it is just dead, right? I cannot do anything. But from time to time, we may make some mistakes. Okay? How many bits are there in my main memory? How many bits are there? I have 2 gigabytes of 2 times 2 to the power 30, okay, times 8. I have this many bits in my main memory, and there is no guarantee that each bit is going to hold its value. It's going to be 0 and 1. From time to time, sometimes those zeros could be 1, and from time to time from those values could be 0. Okay, there is a probability there. It happens once every day, okay, in my main memory, that some of them is going to switch. Okay, so in that case my operating system might cause some problems. So they do this kind of stuff. There are some watchdog processes. These processes run from time to time. They try to see if everything is working right. If they see that something is missing, for example, my Windows Explorer, it is the Explorer that gives me this interface, my files and etc., right? So it is missing, it is not running. So it just starts it, or it sees something else, it just starts it. Okay, so watchdog timers are used to handle those kind of stuff. But if your timer is completely gone, then you cannot do much for regular operating systems. But for specialized...
But don't we have like error correction, sir?
Don't you have what?
Error correction in like memory and disks and stuff like that.
Yeah. But I mean, if the whole memory is gone, you cannot do anything. I mean, memory correction is good, or the error correction is good if you know that your memory is going to function in order, okay, your function properly after that point. Whatever error happened, it happened temporarily, okay. If the error continues with your memory, then you are toast. Okay,
Yes.
Unless you have a very specialized machine. For example, the computer on that Mars rover, Perseverance, okay, it has 2 or 3 CPUs. One is backing up the other one. Okay, there are hot components that are running in parallel, so it has 2 CPUs. Actually, it has 3 CPUs. This is the main CPU running. This is the backup CPU running, but this one is running exactly the same thing as this one. Okay, if there is a problem happening with this, the system switches to this one. This is hot swappable, hot backup, and this is the cold backup. This doesn't run anything. Okay, and there is a problem with this one. Now I can turn to this CPU, but this is a very specialized machine. Okay, the CPU for that rover, the computer system for that rover is at least, it costs at least, I mean, including the development and everything, at least $10 million. It's a very small machine, but because the environment is so tough, you have the radiation, right? When the particles from sun comes and goes through your chips, it does that. Some of your bits will switch from 0 to 1, 1 to 0. Okay, sometimes it's going to permanently damage your computer. So for those kind of cases, then you have those kind of operating systems that think that any part of my hardware can go bad. But in that case, you design your operating system that way. But our operating systems, Windows operating systems, are not designed that way. We trust our hardware. If the hardware doesn't work, then we buy a new one, right? Of course, you cannot do the same thing on Mars. Good. Any other questions? No questions. Let me move on. I have shown you a simple bus structure of a typical computer, very simplified one. Okay. Well, in real life, the picture is not that simple. The picture is more like this. Okay. I have two core system. They have their L1 cache on the cores. Then I have this L2 shared cache. And I have my GPU cores. Okay. These are the CPU cores and this is the GPU core. The GPU core communicates with the graphics controller using a special PCIe bus. PCIe bus is this peripheral component interconnect express bus. It's a very fast bus, but I don't want to share this bus with anybody else. I have a specialized bus for the graphics graphics card, so that I can show my graphics very efficient and fast way on my screen. So if I am running 8K screen and if I like to draw 200 frames per second, this would be possible because all the bus belongs to the graphics subsystem. And I like to do the same thing with the memory. I don't want to use the memory on the same bus as the other I/O devices. So usually for these kind of fast hardware components, modern computer systems, they introduce specialized buses or the dedicated buses. Okay, then this part of my computer hardware is connected to the platform controller hub using this DMI bus, direct media interface. Okay, DMI. And this part of the hub is connected to the other PCIe slots. If you like to add more controllers to your system, you install them into these PCIe slots. But as you see, all these PCIe slots share the same DMI bus to connect to the CPU. So they are going to be much slower than your graphics hardware or the memory hardware. Okay. And then the other specialized controllers such as the Gigabit Ethernet or the USB Type-C stuff, USB Type-A stuff, your hard drives, they are connected to this one. So this is a typical modern computer hardware architecture. And all these resources has to be managed by the operating system. Of course, we get lots of help from the hardware. Without getting help from the hardware, this wouldn't be possible for the operating systems. Okay, any questions? Okay, so there are some bus types, USB, Universal Serial Bus. Okay, with the USB 1.0, it was very slow. Okay, like 12 megabits per second. And USB 2.0, it gets faster. With the USB 3.0, it is very fast nowadays. Okay, with the Type-C, I can connect many devices at the same time, of course, and it is very fast and reliable. I can even connect my screens using the USB Type-C ports. This SCSI small computer system interface, it used to be a very fast and reliable I/O interface. Okay, it used to be for the fast disks or the scanners, and this used to be a very fast connection speed, 640 megabits per second. Nowadays we are doing much better than that using USB 3.0. Okay, from now on I guess it's going to be all wireless instead of having these physically connected buses. we are going to have wireless interfaces, and our peripherals are going to be connected to the computers using the wireless interfaces. Of course, this cell phone business is driving it, because with the cell phones, we don't like these kind of ports. Okay, these kind of ports are making these cell phones sensitive to dust or the moisture, or it is difficult to produce these kind of physical ports. Okay, so instead of introducing these kind of physical ports, some of the cell phone makers actually they abandoned this jack, the headphone jack, right? Or they are trying to abandon this charging ports too, to make it wireless charging. So if these kind of devices are available, of course our PCs are going to use the same interfaces. Okay, so this is the kind of overview of computer hardware. Okay, if we are the operating system software, and if we are going to manage the hardware, then we need to know about the hardware. That's how much we are gonna know about the hardware as far as operating systems are concerned. And from time to time, maybe we are going to talk about hardware. Let's talk about this booting the computer. Actually, it is important to know what's going on when the computer is booted, because that's when the operating system starts running. Okay. For every computer, there is a special software called BIOS, Basic Input Output System. Okay, at least it used to be that way. Nowadays it is a little bit different, but for the sake of pedagogical reasons, let's assume that we have BIOS. Okay, BIOS, Basic Input Output System. When the computer is booted, it first starts. This Basic Input Output System is started. So in a way that it is our first operating system. The task of this BIOS is not exactly the two things that I have told you, resource management and the abstraction of the hardware. The task of this BIOS is very simple. It checks how much memory we have in hardware, and it checks if the keyboard is connected, screen is connected, okay, and it checks what kind of devices are connected to my PCI buses, and etc. And then after doing that, it makes a note and it records all that information to some memory location, and then it finds the boot device, usually a disk, and it reads the first track of that disk and it executes whatever it offers. So whatever the first track of that boot device should be part of my operating system. Okay, first sector from the boot device is read into the memory and executed. That's the task of the BIOS. Finding the first part of the operating system from the disk, loads it to the memory, and executes it. That's booting the computer. The rest belongs to the operating system. What does the operating system do? Okay, it's when it starts execution. Okay, that would be the first process. It sets up all the process tables. It sets up all the interrupt handlers. It sets up all the system call handlers. It sets up everything about the memory and etc. Users, that kind of stuff. So that first part of the disk, the first sector, is very important. If you are doing something harmful, if you are writing a harmful software to a computer, if you are writing a virus, for example, that first sector would be a very good place to write your virus, because the BIOS first reads it. So if you replace that first part of the disk space or the sector with your virus, okay, BIOS is going to read your virus, it will put it into your memory, and now you have the control of the whole computer. Now you can go ahead and read the operating system. You are reading the operating system in a controlled way. You are not going to give full control to the operating system, but you are going to fool the user into thinking that the operating system is booting, but somewhere in the memory your virus is alive. From time to time you will control the CPU. From time to time you are going to do whatever you need to do as a virus. Okay, so that's why that first sector has to be protected very, very carefully. Okay, there is no way that you can write to that first sector even within the operating system. It has to be a special code. Okay, and to make things even more secure, there is a new version of BIOS. It's called UEFI. It is more secure, it is faster, and it supports more hardware. Okay, good. Booting the computer is important to understand what operating system does actually at the beginning and how it starts. Okay, so that's it for the hardware talk. Let's talk about the types of operating systems. Okay, many types of operating systems, and most of them actually we know, and you are going to see that we cannot draw very clear lines between the operating system types. There are many overlapping areas of the operating systems, and history-related classifications between the operating system types. And we are gonna try to talk about each of them. First, let's start with the mainframe operating systems. Okay, we said that the mainframes are the first types of computers, and the first type of operating systems are mainframe operating systems. Today, we still have mainframes, room-size, very large computers. On those computers, there are literally thousands of disks. Okay, and we keep hundreds of terabytes of data on those disks. It is not unusual. Okay, so why do we need such large computers with many disks and very large amounts of data? It is needed for batch processing, transaction processing, and time sharing systems. For example, for a very large airline, to process the tickets, okay, you are selling thousands of tickets every day, and each transaction is similar to each other, but it has to be handled very carefully. Or if you are a bank, okay, let's say you are one of the largest banks of Turkey. You have 10 million customers, and each one is doing tens of transactions per day. So who's going to handle all this stuff? The data is so large. There are many transaction requests coming in, and your workers are causing lots of transactions. So all these transactions are handled by these kind of mainframes, and you need operating system to handle these kind of transactions. Okay, so batch systems are similar to very lengthy scientific calculations. You are trying to calculate the static calculations of a dam or the large building. Okay, so that's called the batch system. Okay, so some example mainframe operating systems: IBM OS 390. Linux or Unix variants are becoming more popular. Okay, so some examples of the mainframe operating systems. So the mainframes are very large computers. Nowadays they are large because they need very extensive input-output capabilities. Okay, go. It looks like I am out of time. I think I will stop here, maybe, and tomorrow maybe I'm going to start over again the operating system types, and we are going to finish up, and I think we can start talking about the next chapter maybe tomorrow. Do you have any questions before I end this today's lecture? Are there any questions? Okay? Then I will see you tomorrow. Please read your book, chapter 1. Read the whole book. It's a very nicely written book. That guy, Tannenbaum, is a very well-known computer scientist, and he knows how to write textbooks. Read the book, and in fact, start reading the next chapter too. Okay, I will see you tomorrow. Have a nice day.